right? Because most of the stuff that you're going to need is already up there. If there was a steel mill already up on the moon, I'd say steel every day. So we made all these foam materials, and we found out that, holy crap, the strength is equal to some base number multiplied by an exponential decay of the porosity. And that's what happens. The water to cement ratio controls the pore space. And that's why we lower it so often. And the pozzolans, because they're a secondary reaction, they go on and they fill that reduced pore space. And they reduce it even further. And so what we're doing with our concretes is we're densifying them. We're taking the space that's void and we're making less of it, and then we're making new shit to go and pack it full. Okay, that's what we do. By chemical reaction engineering and an understanding of what's going on. And then we take our precious concrete mixture that we have given birth to, a piece of paper. We've nurtured it through its early days of trial batching. We've probably done a couple of yard batches. And then we turn it over to the operations people who, even worse, turn it over to the contractor. In order to get any of this benefit, the concrete has to be placed properly and cured properly. What's curing? We talked about it, right? What do we do in the world's worst sauna? We prevent any water from getting away. We keep all the water in the concrete so that it's there to hydrate it. One of the coolest experiments in this course, which we'll not be able to do, is we cast 3 cylinders. We put one of them in the world's worst sauna. We put one of them and make the world's worst soup, which is we put one in the water, and then we put the water in the oven. And then we take its little buddy. We don't put any water there. Put that up to about 400 degrees, turn it on. I hang around, write some paper or something, come back down, turn it off, and then the next week we break it. The sample that was wet in the world's worst sauna, say 3,500 psi. The sample that was in the oven at 400 degrees but was in the water, be 5,000 psi. And the one that's in the oven without any water, if we do it just right, it doesn't have any strength at all. All the same concrete. We cure it differently. You can see now why I'm upset. You have to take my word for it now. You don't have to take my word for water cement ratio, right? We built our curves that look like the ones that are in the design books. Curing is fundamental. And you need to have the concrete cured in order to achieve any of these properties. If you allow the concrete to dry, even if then you subsequently re-wet it, it's not the same, because there's spaces that the water molecules are too large to get into now where they were when you mixed them. So it's very important. We have some packing defects. Remember we had a big bubble in one of the cylinders? So if you don't consolidate the concrete during construction, you weaken it. Not only that, can you imagine if that was in seawater and the tide was coming up and down? Chloride ion, salt water would stick there all the time. That little piece of that bubble would always be full of chlorides. And so we're going to put more chlorides in. When we talk about crumbling and failing infrastructure in the United States and in most of the developed world, we mean the chloride ion-induced corrosion of embedded reinforcing steel. Almost always, that's the root cause. Why did we replace bridges prematurely? Because the corrosion, the reinforcing steel. Anybody driven along Broadway Avenue recently or walked along it? Right? Every single joint is deteriorating. The bulk of the concrete's okay. So what's happening at the joints? They were cut too early. And now instead of having just water trying to get in this direction, it can also get in 2 directions at the corners. That is causing premature deterioration. That road wore out faster than it should have, not because it's not strong enough, but because it's not durable. And we end up with our hands on taking concrete, and it's a rocket, right? You put cement and water together, there's no going back and say, I didn't mean it. It's an irreversible reaction, and it's going forward. You have to get the concrete in place, cured, and properly consolidated, and you will be able to use those materials wisely. So one of the things that we would do is that we would take 2 cylinders, again, same day, we cast one, it hasn't gotten cold enough yet, we put one outside. Then we put 2 outside. Then we quickly bring one in the next day, or the next week, and it's solid ice, it's lots of strong. Compressive strength of ice, about 7,000 psi. Then we let it thaw, and we find out, like, oh crap, it was the ice that was giving us the strength. If you allow the concrete to freeze before it gains an initial set, it's junk. There's no recovering it. You push it over and start over again at great cost. So cold weather concreting, you need to keep the concrete from freezing. Try to think of what else we can cover in the time that we have available. So, it's odd. Hey. Okay. All right. May or may not turn itself back on. Because of the properties of concrete, that it comes to the site frequently as a plastic material, it needs to be protected. That's why we build forms. If you remember the one beam that we did cast, the bottom form is made of wood and the sides come off, and we can leave the bottom in place. Why is that? Because the strength of the beam is dependent on the strength of the concrete, right? And it's going to take some time for that strength to gain. So when we go to place the concrete, we have to build a mold, a structure called formwork, or if you're Canadian, false work. You build it, and it's the mold that you cast the concrete in, and then when it gets strong, when it sets, you can take all the sides off. Right? We've got a condition in our form, when we cast this with concrete in it, you have a pressure exerted in this direction just like it was full of water, as well as a pressure in this direction, right? This is when it's a liquid. Once it solidifies, solids don't exert hydrostatic pressure. They only have pressure going down in that direction. So if I've shored up a beam that I've cast, I want to be able to move the sides of my forms off and fly them up to the next level. But I'm going to have to keep my shores in place for some time until it's strong enough that it won't fall, it won't deflect excessively because it's weak. So I want my forms to be built in such a way that they are removed more readily. Because if you were going to build the when you're building the structure, if you're building a concrete frame like the building that we're in, and as you multi-story, there's a big structure going up in new one starting in Chicago. It's just they're breaking ground now at I think it's 82 stories or something ridiculously relatively high. They're going to want to do 2 floors a week. And if they can't move the forms, then you can't do 2 forms a week, right? And if you take a look at that collapsed structure in New Orleans, you will see that there's posts still left behind holding up what's left of the structure. We're just not sure what condition they're in. So we need to understand that that formwork has to be designed to take into account the fluid pressure of concrete. Similarly, if we build a pavement, can we drive on it the next day? You can if you make it strong enough, right? Typically you can't. It takes a long time. So how do we overcome that particular problem? One of the ways we can do that to accelerate construction is to build elements of our structure somewhere else, bring them to the site, and assemble them, which we call precast concrete. So cast in place concrete means that you brought it to where the structure is going to be and you filled up the forms. Big advantages of doing that, right? Because it's pretty hard to move a 300-foot beam on the highway, but I can cast one in place in one day. But precast allows me, instead of having to build everything in series, I can run it in parallel. Anybody taking scheduling yet? But you can imagine if we were all to decide that we wanted to make, I don't know, what are we going to make? We're going to make a whole bunch of hamburgers and hot dogs and various things, but we only have one small grill. And each one of you has a different type of bratwurst that you made of the deer that you murdered mercilessly without even a warning shot, which is what they deserve, being merciless, that is. We would all have to wait, right? Because you'd cook your bratwurst, then you'd cook your bratwurst, then you, and eventually we'd get to the point where they're all done. But if everybody has their own stove or burner, all of a sudden we get it done in a very short period of time. So you can imagine if I have to build a floor by casting the columns, putting the forms on, or taking the forms off, or keeping them on, sorry, build the slab, fly some of those forms, move the columns up, pass new columns. I can't build the third floor until I build the second floor, right? Because I can't tell gravity to, take a chill pill and we'll be with you in a minute. It's always going to be pulling stuff towards the center of the earth. But if I have to wait 4 or 5 days or 3 days for my strengths to come up, then that takes time. If I want to build something quickly, I can build the elements somewhere else, bring them to the site as hardened concrete, and assemble them. Precasting. Why don't we precast everything? Because we can't move 300-foot beams. And one of the big advantages of concrete is we can post-tension it. Right? We can put tendons in the concrete, cables, and then when it's hard, and gain some strength, we can pull on those cables and put it into compression, pre-stress it, so that it, if you see an empty tractor trailer going down the highway, you'll see it's cambered up, right? Because it's cambered up so that when you load it, it's flat, it's been pre-stressed. Do the same thing with concrete. So we can place massive panels that you could never move. But if you're building an apartment building or a parking garage, you can pour the footings, come in, stick a precast panel or precast column, 1, 2, 3, 4, put the beams on, 1, 2, 3, 4, stack the slabs, precast hollow plank, pre-stressed slabs. On those, there you go, get the building built already. I could do a floor every day. Just keep right on going. Need to be careful because it's very easy to tip it over. But there's different reasons you would want to do that. Precast concrete's usually more expensive because the kind of trucks that you can haul the cast concrete in. But it's way faster. And sometimes fast has a value of its own, right? What did Stalin say? Sometimes quantity has a quality all of its own. Speed sometimes is what you want to do. So precasting concrete can be done in a factory. What do we do in a precast factory? We take the concrete, we mix it up, pour it in the forms, we put the forms in the steam room, which is just probably the world's second worst sauna. Because that will kill you fairly quickly. It'll pull all the heat out of you. This one you blast in hot, wet air at 140 degrees. It won't kill you. You probably live longer. But the concrete heats up to 140 degrees. And it starts hydrating and it gets going. And you can take concretes, if you can jacket them like that are 80% slag and have the same strength as though it was 100% cement. It makes a huge difference. And it's used sometimes in combination. When they built the Hastings Bridge structure down on the river in Mississippi, Mississippi River at Hastings, they precast the panels, they precast the main bridge girders on the side of the river, and then they lifted them in place. If you drive up and down the highway, you'll frequently see people moving concrete girders for bridges. They bring them in, they stack them. It's very rapid construction. It's more expensive. That's why they're oversized loads, and they've got trucks and they get special permits and everything else. So it all depends on what you're trying to achieve. But one of the things you can do with precast, because you have control of the curing conditions, you can get denser concrete. Denser concretes are more durable. So that is a desirable thing to do. Sometimes you get some problems with performance of concrete. How are we doing for time? Not too bad. Get problems with performance of concrete. And so those problems are usually related to an issue with the wrong material or the wrong equipment or not enough of a material or equipment. A cold joint occurs in a structure when there's a delay in the delivery of concrete. How come you might get a delay in the delivery of concrete? I'm going from a ready-mix plant to this point of placement. What might happen?
Transportation issues. Traffic,
right? Someone gets into an accident, the vehicle breaks down. Also may have had somebody, I may have a series of vehicles that are going to do all my delivery, except somebody's having a problem with quality, and we can't get the concrete right, and the trucks are stacking up at the site, but it's not your site, it's someone else's site. And as they sit there and do nothing, we plan them to go back to the plant, get concrete, and send it to you. Cold joints can occur, and they're very, very risky because the structural engineer will want to know that the concrete, when it was replaced, was adequate. So just like when we rod the cylinders, you want to make sure that the vibrator is going in to the original layer to try to close those cold joints. You want to be careful about concrete color. Every specification you ever see will have a little throwaway line in the concrete section that says you shall use the same brand and type of cement throughout the project. Sounds pretty easy, right? What are they trying to tell you? They don't say it should come out and say it, but they don't. They want you to have it the same color. If you are stupid enough to take cement from, say, in the Twin Cities area or in this area, take cement from Lehigh's mill in northern Iowa, and then take cement from Dundee's mill in southern Iowa. They're pretty close, except one is the darkest cement in the market and the other is the lightest cement in the market. And it happens to lots of people. You deliver the first half of a driveway today and the second half tomorrow. One of them is really pale buff gray and one of them is steel blue gray. Surprisingly, the owner is not pleased. There's some things we can do with concrete we're seeing more and more frequently, such as coloring concrete. When you color concrete, you put in a pigment. We have a little lab that does that too, but anyways, that pigment can cause some significant problems. So you need to be aware of that, of those problems. Well, there's a good picture. Where is that? This is see up here that beam. Can you see all the cracks in it? That's an alkalisilica reaction. So you can do a lot of architectural things with concrete, and more we're seeing concrete as the final finish. And it's not magic. You still have to have the right concrete, and you have to cure it and treat it properly. In 2003, a client of Sem Stones received the the Ready Mix Concrete Association of Wisconsin Grand Award for Decorative Concrete for a restaurant up near Turtle Lake. Really beautiful. I mean, it looked like you were walking on slate and everything else, and it's just gorgeous concrete. So they got some big fancy award. So who got to go to the award ceremony? Well, the area manager for the plant, salesman, of course, and my boss, who was the owner. Nobody else wanted to come out and see it in the spring with me because it had not been adequately cured. So you can imagine an outdoor patio, people serving them beer. You don't want anybody to slip, so you throw a little bit of salt down, and it was falling apart. Surface was flaking all over the place, called scaling. So no, at that point there was no great award ceremony. There was just Kevin, go up there and figure that out. And I looked at it and took a core, ran a few tests, and said, try curing it next time. So you have to be careful. There's award-winning work that was junk 6 months later. All because the artiste who put the beautiful, and it was, I mean, I couldn't have done it. Right? I mean, I would say, like, gray concrete, that's good. It's got some blotchiness over there. I like it. But it looked, you couldn't tell you weren't on stone. But it took so long to do that on a windy day that it didn't cure. You can get some problems with plastic concrete when you're constructing it. If you put concrete down, it will bleed. So water will rise to the surface. It's actually the particles are falling and you'll see that bleed water sheen, and that will go away. And when it goes away, it's transformed from a liquid when the particles are falling to a solid where that water, the particles don't fall anymore. If the rate of evaporation exceeds the rate of bleeding, in other words, the rate at which water is appearing at the surface is slower than the rate at which it's being taken away, the surface will dry, and you'll get plastic shrinkage. Plastic shrinkage, this is all in your design and control mixtures, by the way, if you want to reread it. But plastic shrinkage occurs when the concrete is still a plastic. Cracks are short, they're discontinuous, they're wide at the surface, and they narrow very abruptly, and they're all in the same direction, perpendicular to the direction in which the wind was blowing. That's the key diagnostic for plastic shrinkage, is that the cracks are only in one direction. Slabs that are on soil and walls and all sorts of other things, we need to control shrinkage. You've probably all seen the Seinfeld episode that talks about concrete, where George is very concerned if they know about shrinkage. No? Yes? No? Anyway. If you have a piece of concrete, as it reacts and sets and dries, it will get shorter naturally as the particles, as the water molecules pull the sheets of calcium silicate hydrate together. That shrinkage will cause a strain, which results in a stress no different than if you were compressing it with a machine. If we don't account for those shrinkage stresses and curling stresses, because it'll dry more on the top than on the bottom, and so it will take on a curled shape, then the slab is going to crack. So we intentionally installed crack control joints. We cut them into the sidewalk, we cut them into the slab, so that we put the cracks where we want to. So from a functional point of view, a random crack that has occurred because we just let it shrink and a saw cut joint are the same thing. From an aesthetic point of view, one of them looks like they did it on purpose, and one of them looks like it's a big disaster. And so you want to cut your control joints, and typically you want to be somewhere between 24 to 36 times the slab thickness in inches. Or sorry, slab thickness doesn't matter. We used to say 2 to 3 2 to 3 times, the joint spacing in feet is 2 to 3 times the slab thickness in inches. The reason we do that is so that we control the cracking. We get as little out of joint or uncontrolled cracking. We get lots of cracking. We just think that they're meant to be there. If we're not careful, we will get mid-panel cracks. A crack that is dead center between the two joints or close to it is a sign that the joint spacing is too high. It should have been reduced. Of course, it's also too late, right? So you need to know that. And that, when do you cut the joints in? As soon as you can, without damaging the edges of the cut surface. So you have a window, just like you had that window from when when it starts to set to when it's so hard it can't be finished. You have a window of when to cut these saw cuts in. And if you miss the window, it will crack. And the worst situation, I've seen it, it's fascinating to watch. You're cutting with a saw, you're cutting a thin, cutting down a third or a quarter of the thickness to create this plane of weakness for the crack. And then the crack starts appearing in front, and it runs in front of the saw. And it's only about a foot or two in front of the saw, but it doesn't matter, it's too late. You can't do anything to fix it. And that's a skilled trade, but you need to remember that that may mean that people are there until the slab is done. The proverbial story of we deliver a load of concrete from Semstone to a house, and there's nothing there. There's no forms, no nothing, and the guy who lives there comes out and says, "Oh no problem. My wife works for Lunda. Just drop it over there in the corner, and she'll finish it she'll work on the rest of it when she gets home." There is no such thing, right? Concrete waits for no man. Here you go. You got a T-shirt that says that. So we've got a lot of issues that go on with concrete construction. Some of the particles are not good particles. They will be damaged themselves by freezing and thawing, or they'll dissolve. If you ever see a wall and you'll see one single rust stain running out of it, see it a lot in barrier walls and that sort of thing. That's not rust, that's an iron oxide, an ochre, that's going back into solution, and it's dissolving itself in the concrete. pH is relatively high, and so that's an aesthetic defect. If the people know what they're looking at, that's not a problem. If they don't, you can really run into big trouble. Slabs, if you walk into say Costco or who else is doing it? The Walmart, and the slab, you walk in, the slab is really shiny. Have you ever seen that? And that's because we take a steel trowel and we squeeze the water out and we burnish. We rub the surface. And the reason that it turns dark is because we are transferring iron from our trowel onto the surface. You know, the trowels will wear out eventually. The iron's got to be going somewhere. And that iron is why concrete is gray and not white. Iron oxide makes the surfaces gray. So that dark, densified surface is a sign of power troweling. We will also see this if we're placing concrete and we cover it with polyethylene or visqueen, is the old manufacturer's name. If you put material down onto the concrete surface that is a visqueen, then and it's sealed perfectly to the surface, then the amount of oxygen present at the surface is the same, and the iron is low, and the iron will all go to iron plus or iron 3 plus, and that's a dark color. If you have one little fold that there's oxygen there, that place will go to iron 5, and that will be brighter. And that surface will take on that mottled appearance forever. So, if you are going to be placing concrete and you think it's going to rain, and you may have to cover it, you're always better to cover it with a fabric than plastic. or just the fabric, right? Not a lot of drying is going to go on while it's lightly raining. So be careful of that. We saw broom texture. We talked about some tools, running out of space in your head to cram things into. We're going to meet on Monday. And on Monday, we're going to walk through this building, and I'm going to teach you how to read masonry walls so you can tell a lot about the structure, how it works. We'll combine that with looking at, we have a really nice model of a cavity wall just like the building here, and how the structure works and what those materials are so we can get caught up. And that's our plan for dealing with our COVID-19 shutdown. And I think we'll be back, at least that's what we're told right now, right? You all saw the same memorandum from the Chancellor that I did. We will all be back, at least for some time in the winter and in the fall. But this class is much more about teaching you vocabulary and some understanding of how the materials behave than anything else. Hopefully it's been all right so far, and we are going to finish it up well in the online. We're probably going to have a couple of mixed designs to do, and then I will have them taken to our lab in the Twin Cities, and we'll videotape what they look like. It's not quite the same thing, right? But there I don't have to lift anything heavy because I have people work in the lab and lift things heavy. I took the other samples because remember I said the strengths really seemed kind of high? So I took the other cylinders back to our lab in Mendota Heights. No, they weren't high. That's what we're getting from the rest of them as well, 5,000 and 6,000 psi. So good job. What does that tell you about that water to cement ratio versus strength curve that we have in the textbook? It's not accurate, right? We designed for 3,000, we're getting 6. We're designed for, technically for 4,000, we're getting 6. And that's because it's older data. More modern cements are more reactive. Anybody have any last comments they want to make before we close out our penultimate in-person session for this class? All right. Just keep your head up. From a scientific point of view, it appears that we're seeing a number of good candidates for vaccines. That we could, as quickly as this became a big problem, go the opposite direction. So just hang in there, stay safe. Anybody going home for Thanksgiving? All right. Whereabouts to? Milwaukee, all right. Where you, I'm sorry? Oh, okay. So, and then coming back here or not, as the case may be. If we run into trouble, if you're having a problem, and in fact, from a human being point of view,